All right, let's dive into something that sounds like it's straight out of science fiction. We're going to talk about how scientists are trying to literally tie the world's smallest knots to build a computer of the future. It's a wild idea, but to really get it, you first have to understand the massive problem they're trying to fix.
Here's the one thing you need to know. The world's most powerful computers are also the most fragile. I know, it sounds like a paradox, right? But that single idea is the biggest headache in all of quantum computing. So let's talk about that. Because before we can get to the world-changing stuff, we have to look at quantum computing's biggest flaw.
Okay, so the big problem has a name: quantum error, or decoherence. The easiest way to think about it is like this. Imagine a quantum bit, a qubit, is a perfectly spinning top. All the amazing information it holds is in that perfect spin. But here's the catch. The slightest little thing, a tiny vibration, a change in temperature, you even breathing near it, can make it wobble and just fall over. And poof, all the information is gone, instantly.
That incredible fragility, that's it. That is the #1 reason we don't have large-scale, world-changing quantum computers yet. This is the big puzzle that scientists everywhere are in a race to solve.
But what if trying to make a more stable spinning top is the wrong approach? What if there's a way to store information that just doesn't care if it gets bumped around? Well, that's where this really clever idea comes in, a solution made of knots.
So the question is, how do you build a quantum computer that doesn't fall apart? How do you make something that isn't so ridiculously fragile?
Enter the topological qubit. Okay, so forget the spinning top for a second. I want you to picture a braid, like a braid of ropes. Now, the information isn't stored in any single one of those ropes. No, it's stored in the overall pattern of the braid itself, the way the ropes are all woven together. So you can wiggle one of the ropes, you can jiggle it around, but the braid itself, it stays the same. The information is protected.
And that right there is the key difference. A regular qubit, it's fragile. It's that single spinning top. But a topological qubit is robust. It's like a whole complex braid. It's naturally protected from all that outside noise because the information isn't in one little spot. It's woven into the very fabric of the whole thing.
Now, this idea is so powerful, so revolutionary, that it has kicked off a global race to build one. We're talking tech giants, university labs, everyone trying to be the first. This is not just a cool theory anymore.
And just recently, Microsoft made a huge announcement. They basically said, "We've done it. We've built a chip, the Majorana 1, that we think can be the world's first topological quantum processor."
And take a look at this. This isn't a computer-generated image. This is a real prototype quantum chip. I mean, the level of precision here is just mind-boggling. They're working at a microscopic level to build these things.
Okay, but whenever there's a huge claim like that in science, you know what comes next, right? The big question. Is it a real breakthrough?
And yeah, the scientific community definitely put it under the microscope. See, to make these quantum braids work, you need these super exotic particles called Majorana zero modes. And in the official peer review, the editors at the journal Nature basically said, hey, the results you have here don't actually prove that you've created these particles. So the jury is still out, to put it mildly.
But that's not the end of the story. Other top researchers like Sankar Das Sarma have a different take. He's basically saying, look, this isn't a simple yes or no thing. He argues that what Microsoft did is a massive step forward on a problem that is incredibly difficult. It's not like flipping a switch. It's a long, complicated process.
So with all this debate, why are companies and governments pouring billions and billions of dollars into this? Because if they can get this to work, the payoff is absolutely enormous. We're talking about a multi-billion-dollar future.
Get this. Right now, in 2025, even with the tech still mostly in the lab, the market for topological quantum computing is already valued at $3.7 billion. That is a ton of money for something that's still being figured out.
And it's not standing still. The projected annual growth rate is 21.5%. That's how much confidence there is that this is going to be huge.
You fast forward to 2034, and the market is projected to be worth $21.3 billion. I mean, those numbers are just staggering. They tell you just how big the expectations are.
So what's all the fuss about? What could we actually do with this technology? Well, we're talking about things like discovering new medicines and materials from the atom up, creating things like self-healing bridges, completely revolutionizing sustainable agriculture, making financial modeling way more accurate, Oh, and building incredibly powerful new AI. Just, small stuff like that.
So, the potential is obviously massive. The scientific debate is happening right now. The big question is, what happens next? What's the actual plan to get there?
Well, companies like Microsoft have laid out a roadmap, and it's pretty logical. Step 1, perfect a single qubit device. Get one working perfectly. Step 2, build a 2-qubit device so you can actually demonstrate that braiding we talked about. After that, you use a small group of them to learn how to spot errors. And finally, step 4 is to scale it all up to larger systems that can fix errors on the fly. It's a long road, but it's a clear one.
And all of this kind of brings us to one last big question. The journey to get there is obviously super complex, it's full of debate, and the technical challenges are huge. But it really makes you wonder, could the solution to humanity's biggest problems be tied up in a quantum knot?